In this video, I'll be demonstrating that the operations of adding, multiplying, and even factoring work the same way with trig functions as they do with regular variables. First, I wanted to show that there are actually two ways to write the exponent on a trig function. The most common way to do it is actually to write the exponent right after the trig expression, the sine, cosine, or tangent part, but before it determines the variable it's going to be using, whether it's x or theta, whatever the case may be. This is the same as if you write the entire trig function with its variable and set parentheses and then put the exponent on the outside. So this will be used sometimes as well, but this is the most common way of writing a trig function to the second, third, fourth, whatever power you have. Put the number right in there in between. For our first operation, we'll look at adding and subtracting trig functions. This will follow the same rules you've used for adding and subtracting like terms for variables. For example, you cannot add two like terms if they are not both using the same variable. You couldn't add an x and a y, for example. So for trig functions, you can't add sine and cosine or sine and tangent. It has to be the same trig function. Another rule is that the variable they're using with the trig function must also match. So it's not enough for it to just both be using sine. In this case, sine of x would not be the same as sine of theta because these variables will be representing different numbers. So they're not like terms if they don't have the same number in there inside of the same trig function. So you have to have the same trig function and the same variable. And then the last thing, just like with adding other like terms, you have to have the same exponent. So you couldn't combine something like sine squared with sine in the same way that you can't add x squared plus x. You have to have the same exponent on those trig functions as well. So now I'll show you a quick couple of examples to demonstrate this. So here we have 3 sine of x plus 2 sine of x. And if it helps you, you can honestly just rewrite this. These are like terms, sine to the first power of x, sine to the first power of x. So you could just think of this as 3x plus 2x. If I gave you this problem to work out, you would say you have like terms, so add the coefficients and you get 5x. This is the same thing, so we're going to get 5 sine of x. Here we have some like terms and some that are not like terms. For example, I cannot add the cosine and the sine terms because they are not using the same trig function. However, I have a cosine to the first power of theta and a cosine to the first power of theta. It's using the same variable, it's the same trig function, and it's the same exponent. So these two outside terms can be combined. So I would add those two only. 2 cosine plus 1 cosine is 3 cosine. And then anything that is not a like term just has to stay separate. It doesn't get combined, so I leave it as its own term of sine of theta. And then one last example, all of these are using tangent. However, this one and this one are both raised to the second power, so these are the only ones I can actually combine. You have to have the same exponent. So 4 tangent squared minus 1 tangent squared is 3 tangent squared. Notice that the exponents are not changing when I add these. And then the other term that was not a like term with the other trig functions has to stay apart as its own part. Now we'll look at the rules for multiplying and dividing trig functions. Again, this follows the same rules as multiplying or dividing variables. So if you multiply two terms with the same trig function, you just add the exponents. In the same way that if I said x squared times x to the third power, you would get x to the fifth power because you add those exponents together. If you are dividing two terms, or if you have a fraction is just a way of writing division, then you subtract the exponents. So the one on top minus the one on the bottom. Again, it has to be the same trig function though, and then you're just changing the exponents accordingly. Any other coefficients, you multiply or divide those numbers normally. That is a separate part of the trig functions being combined. So in this first example, I have 2 cosine cubed times 3 cosine of x. You do not need like terms or anything when you're multiplying and dividing. That's just for adding and subtracting. So I'm going to do this as two separate operations. I'm going to do the 2 times 3. So that's 6. Nothing is changing those rules. We're multiplying the coefficients normally. And then here I have cosine to the third power times cosine to the first power. If they don't write an exponent, there's an imaginary 1 there. So I need to add those exponents since I'm multiplying. So the answer on this one will end up being 6 cosine to the fourth of x. Here I have a division question. Again, you can focus on the coefficients separately from the trig functions. So I have one term divided by one term. 8 divided by 2 is 4. And then here I'm dividing the trig functions. So when you divide two terms, subtract the exponents. I have the third power minus the first power. So I end up with the second power. If you get a negative exponent, or if you have a bigger exponent on the bottom, basically that's what causes that. That just means you will still have a fraction and your leftover power will be in the bottom instead of on the top. So if it had been the other way around, if I had the first power on top and the third power on the bottom, it would have been 4 over sine squared. Now for a look at how fractions are affected when they have trig functions in them. This will follow the same rules as fractions with variables or numbers instead. So when you are multiplying fractions, remember to just do the numerators multiplied together and the denominators multiplied together separately. When you are dividing fractions, you either want to take the second fraction, if it's written this way, and change it to a multiplication by the reciprocal, or it may be written as a fraction itself, so you may want to take the denominator and multiply by the reciprocal of the denominator instead. If you are adding or subtracting fractions, like in this example I'm going to show, remember that you do need to get a common denominator first. So you might have to multiply both the numerator and denominator of each fraction by a number to make the denominators match. So for the first example I'll show you here, if it helps you to remember, this does count as cosine of x over 1. So if they don't write it as a fraction, if it's a whole number, remember it is over 1. I don't want to try and work out this division question as it's written. I'm instead going to show this as cosine of x over 1 times, and then we're going to flip the second fraction or find the reciprocal of it. So then this becomes cosine of x over sine of x. In this form, now I just have a multiplication question, so I need to do numerator times numerator and denominator times denominator. So for the numerator, cosine of x times cosine of x is cosine squared. And for the denominator, 1 times sine of x is sine of x. Nothing else can be reduced here, so that example is finished. For the second example, we do need a common denominator before we can add or subtract the fractions. So the fraction on the left has secant in the denominator, but not cosecant. So we're going to multiply top and bottom by that cosecant of theta. For the fraction on the right, we have cosecant, but we do not have secant. So we need to multiply this fraction on top and bottom by secant of theta. Remember, the reason we're allowed to do this is because multiplying the top and the bottom by secant means I'm essentially multiplying by 1. A number divided by itself is 1. So we're not changing the value of the fraction, we're just changing its form. So now here on the left fraction, I have cosecant times cosecant is cosecant squared. On the second fraction, because I'm going to have a common denominator now, so I can just write this as one fraction, I'm going to have secant of theta times secant of theta is secant squared of theta. Remember, we do not actually change anything in the denominators. You just get a common denominator, and then the denominator stays the way it is for both fractions. So my denominator is cosecant of theta times secant of theta. We're not actually adding the numbers in the denominators. You just have to have the same denominator before you can combine the numerators. So that would be the answer for this example. And the last skill I want to go over is how to perform factoring operations with trig functions. And the rules, again, are the exact same as what you would do if they normally have x's or y's, whatever variable they chose. Again, it can be helpful, a lot of students have found this helpful, to replace the trig functions with a variable. Now keep in mind that if you have different trig functions, you need to use different variables for each of them. So you can't just replace all the sines, cosines, and tangents with x, for example. Each trig function would have to have its own variable to keep your factoring rules in place. For example, on this first one I have written here, we have cosine to the second power and cosine to the first power. We're using the same trig function twice. So if it helps you, you could rewrite this as 4x squared plus 3x. And then I hope you would be able to factor that normally. And at the end, you would just have to go back in and replace all the x's with cosines. But the same rules apply here. So what I want to recognize is that my variable, cosine of x, is in both terms. So this is a GCF. That means I can take out the common factor of cosine of x. And that would leave me with 4 times cosine of x to the first power because I took one cosine out. And then here I'm just left with the 3 because I factored the cosine part out. So you would get the same answer if you continued to work with it using only x's and then substituting back in the cosines at the end. But then this saves time if you can get comfortable with just doing it straight from the trig expression as is. For the next example, here I have a difference of squares factoring. So if I wanted to substitute, I would need to use a different variable for the sines and the cosines. And then at the end, every x would be replaced with sine and every y would be replaced with cosine. But again, I'm going to try to show this using just the trig expressions as is. This is a difference of squares because I have something squared minus something squared. So I know that the breakdown is going to be a plus b, so sine of theta plus cosine of theta, times a minus b, so sine of theta minus cosine of theta. Then for our last example, we're going to use the trinomial factoring approach. Again, for replacing with the variable, if that helps you to visualize what I'm doing here, you could think of this as x to the second power if we decide x is tangent. And then we would have 5 times x plus 6. So this turns it into a more familiar trinomial that hopefully you are comfortable factoring. But I'm going to do it straight from this form, the tangent squared plus 5 tangent plus 6. So we know that when we're performing our factoring steps that we end up with 2 binomials. And the first terms in each binomial also multiply together to give me tangent squared. So in this case, it would have to be tangent and tangent. And don't forget to include the variable as well. It's tangent of x in this case. For the last number in each binomial, we need 2 numbers that multiply together to equal 6, but add up to equal 5. So in this case, my numbers would be 3 and 2. So 3 times 2 is 6. 3 plus 2 is 5. If you distributed this back out or FOILed it back out, you would see why this is the correct factoring of tangent squared plus 5 tangent of x plus 6. So that's it for going over how our operations and our factoring techniques still work for the trig expressions the exact same way as they do when we're just dealing with variables. This will come in handy over the rest of the lessons that we'll be covering for pre-calc.